Shall we start?
Yeah.
Okay. Welcome back, everyone. Our last speaker of the day is Castro from University of Arkansas. He will talk about relative group trisections.
Yeah, thanks. Thank you to the organizers for having me. Very happy to speak. Yeah, so I'm going to tell you about these things called relative group trisections, and everything I'm going to talk about is joint with Jason Joseph and Patrick McFaddin. So the idea is we want to use these things called trisections of four manifolds to encode all the smooth topology of a four manifold with boundary into sort of group theoretic data. And this was done in the closed case already by Aaron Abrams, Dave Gay, and Rob Kirby. So we want to sort of construct sort of a dictionary that goes between manifolds and groups in a nice way. Okay, so just all manifolds are going to be assumed to be compact, connected, oriented, and smooth, and for the most part, four-dimensional. Okay, so and feel free to stop me at any time if you want me to elaborate on anything. But we're going to start off with the closed setting. So we're going to start off with the definition of a GK trisection, and it's a we have a closed smooth four manifold, and we decompose it into three pieces. And each of the pieces is diffeomorphic to k copies of S1 cross B3. So that's like a four-dimensional wedge of circles, right? And then which is right here in this little schematic, is a genus G surface. And one thing I want to point out is that this sort of pairwise intersection here, this is we could think of that as, okay, so here's one of our handle bodies, genus G handle body, HG, why not? And then over here is another genus G handle body, H G prime. And one of the things is that HG union HG prime, this is a Heegard splitting of the boundary of each of the pieces. Okay, so we have this really nice decomposition of the boundary as intersections with the other pieces. Okay, so that's sort of what a GK trisection is in the closed case. And a lot of the times we talk about trisection diagrams. So just like in Heegard splittings, we have Heegard diagrams, we have these things called trisection diagrams. And in the trisection world, we sort of have these three collections of curves, alpha, beta, and gamma. Right, we have a genus G surface and curves alpha, beta, and gamma. And one of the conditions is that each of the pairs of collections of curves, if we look at those without a third collection, they actually give us a genus G Heegard diagram of k copies of S1 cross S2. Right, and let me go back here just to be explicit. Right, the boundary of xi, here's xi, so its boundary is really k copies of S1 cross S2. Okay, so I haven't drawn the green curves on here, but they're on here somewhere floating around. Maybe they do something like this. Maybe there's one. Okay, and then there's a whole bunch of other ones. But if I were to sort of erase the blue ones and look at the red and the green alone, then they would look standard in this nice way. Okay, so this is really nice because now we can draw sort of four manifolds as curves on a surface, which is super cool. And so I want to just give you an example and then sort of tell you how the groups come into the picture. So I want to draw a 2-0 trisection of S2 cross S2. And as I've drawn it, this is just a Heegard splitting of S3. And now when I draw my green curves on it, we get our, like that, our trisection of S2 cross S2. And if I were to delete any of the other colors, then up to diffeomorphisms and handle slides of the curves, we could actually get it to be the same genus 2 Heegard splitting of S3. Okay, so here's what we want to do. We have our trisection surface, and that includes to each of the pairwise intersections. So each of these sort of spokes of of this picture. Right, this part includes to each one of those little legs, and each of those legs is sort of the intersection of one with the other, or with another. Next one goes intersect x2, one intersect x3, and then x2 intersect x3, and this sort of is given by inclusion. And all of these pairwise intersections include into the actual pieces of the decomposition. And then finally, all of the pieces include into your form manifold. So we have this nice sort of diagram, which looks like a cube sort of on its end with all these inclusion maps. And to get to the group theory from the trisection, it's really nice. All we have to do is take pi1 of each of these pieces. Let me draw this in a different color so that it stands out. Okay. Pi1 of all of these pieces. Right, and then all of these homomorphisms are the homomorphisms induced by pi1. Right, and so this is a really nice way to get this diagram of groups from the trisection. And now the idea is we want to sort of go the other way. We want to give group theory information and then sort of recover smooth form manifold topology from it. Okay, so let's start off with some notation. So we're going to say SG, that is just the surface group of genus G. So we have 2G generators in one relation, and then we're going to give these free groups just special names. Okay, so a group trisection of a group G is this following diagram. I should say it's commutative cube. Such that all of the homomorphisms are surjective. And then when I look at each one of these faces, it's actually a push out. And so it doesn't matter which face I look at, but we get a push out. And that's it. So that's what a group trisection of any group G is. Okay. And so we have a couple theorems here. So every smooth closed form manifold admits a GK trisection for some G and K. So it was Dave Gay and Rob Kirby in their first paper on trisections. And then for the group trisections, every finally presented group admits a GK group trisection for some G and K. And so what they prove in their paper is actually, this theorem is actually a corollary of what they prove. What they show is that if you give me a trisected form manifold, so let's say that's a trisection of the form manifold X. Well, by taking pi1, like we just did, we actually get a trisected group G, right? And they call this map G because you're actually constructing a group. So again, let's just take that one. Okay, and then what they also show is that how to construct from a trisected group an actual trisected form manifold X, and they call this map M. They're building a manifold out of that. And not only that, but these sort of maps, if you compose them, they're the identity on their respective sort of sets. And so you can do this construction and sort of get this back the same form manifold. If I start here, go here, and then do that. Okay, and this is really the second thing is really a construction. Okay, and then they get this as a corollary by saying, you know, every finally presented group is pi1 of some form manifold. So we can realize that group trisection in that way. Okay. Cool. So that's the sort of the scene of what we're dealing with. And now I want to start talking about manifolds with boundary. Okay, so I'm going to define a relative trisection diagram for a manifold with boundary. That's fine. So we have the same sort of setup, right? We have curves on a surface. And now one of the main conditions here is that you have a surface with boundary. Denote this by GB. You have B boundary components with B, where B is strictly positive. And not only that, but you have fewer curves on your surface than there's genus. Okay, and then we have this sort of the same standardness condition, but we can't sort of package it in this nice like sort of Haggard diagram terminology. So the standardness condition is that you can do diffeomorphisms of your surface or handle slides of your curves so that any pair of your curves sort of looks like this. Okay, and these numbers are sort of awful to remember, but that's what they are. And again, the green curves are sort of just on there doing their thing. And the idea is this also constructs a form manifold, or this corresponds to a form manifold with boundary with a certain trisection structure. Okay, so this here is a trisection diagram of B4. So this is a 1, 1, 0, 2 relative trisection diagram. Of B4. And this actually comes from sort of perturbing a Lefschetz vibration on B4 that has like a single Lefschetz singularity. Okay, and now what we want to do is take this.
Yeah, can I ask a question? Can you just
go ahead.
Can you just remind me with regards to these 4 indices? What is the order that you're?
Oh yeah, definitely. This is G. This is K. This is P. This is B. And yeah, I'm glad you asked that. So this stuff sort of tells you sort of the interior information, sort of form manifold information, and all of this gives you information about the boundary through manifold. Yeah, and we'll talk about that in a little bit. Yeah, and so we construct a form manifold as follows. We take a disk across our surface, and then we attach these little legs. Just in the other case, we have these little legs, and these are sort of what are called compression bodies. And these are really cobordisms from sigma to a genus P surface with B boundary components. And the idea is like you take this surface, cross it with an interval, and then at some point you start attaching 4-dimensional 2 handles along the alpha curves. Right, so you compress along the alpha curves along that leg. And then you do the same thing over here with the beta curves, and the same thing over here with the gamma curves. And so what you have at the end of here, these are all genus P lower P surfaces with B boundary components. So we're going to glue in this sort of P cross I, where P is diffeomorphic to each of those ends. And so we're going to attach these over here and do that to each of those components. And in the previous case, I didn't explicitly say this, but in the closed setting, sort of this, in the schematic, this part of the region sort of didn't really correspond to the boundary of your piece. But in the relative setting where you have boundary, this is actually just a surface cross I right here. And actually what's happening here is we see that we actually get this sort of surface bundle over S1 happening on the boundary of our form manifold. And I'll talk about how that plays in to everything. Okay, and then
can I ask one more question?
Yeah, go ahead.
So here you're gluing in this P cross I.
Mhm.
How are you identifying these surfaces?
That's a great question. Yeah. So it turns out that there's a unique way to glue this in so that this boundary is a bunch of copies of S1 cross S2s.
Oh, I see. And that's how you're getting, you said you got the surface bundle. Okay, I understand.
Yeah, so yeah, we do that in such a way so that now each of these pieces has boundary a bunch of copies of S1 cross S2s. And then we fill each of them in. With a bunch of copies of S1 cross B3s. And this is unique. Yeah, and that's sort of one of the nice things that like everything in this construction, like you think there would be all these choices to be doing it, but this is all sort of done uniquely. And maybe I'll say it was done by Laudenbach and Pointerou. Yeah, so one of the important things to keep in mind is that I'm just going to write over my drawing. So this is X1, maybe X2, X3, and each of the Xi's is diffeomorphic to S1 cross B3s. And then these are, let's see, this is a surface cross an interval. So that's a handle body, and then we attach 2 handles. That's still a 3-dimensional handle body. So the pairwise intersections are 3-dimensional handle bodies of some genus. Okay. Cool. And now we want to do the same idea. We have this relative trisection, and then we just take pi1 of all the pieces, and we get all this group data. And everything here sort of goes off without a hitch. It's exactly what we want. And again, now the sort of thing that we want is, can we go this way? that map M to construct a 4 manifold from group data. Okay, so we're going to use, again, some interesting presentations for groups. So here we want to sort of keep track of generators which correspond to genus and generators which correspond to boundary. And we just have this single relation. So really this is a free group, but we give it this one presentation. Okay, and then same thing here. This is also a free group, but we give it another interesting presentation. And now there are sort of 4 types of generators. These are going to correspond to boundary as well. These correspond to sort of the standard generators around a genus. And then this one, remember, we had this sort of compression body, which was a cobordism, and we compressed along these curves. I'll just draw a picture down here. So if we compress along, say, this alpha curve, well, that's supposed to bound a disk, so that's not going to give us a generator, but in the cobordism, this curve still bounds, or this curve still exists. So these delta curves are sort of duals to the curves along which we compress. And we sort of have this presentation so that we can keep track of everything. And then we by the time we get to here, sort of everything's going to work out nicely, so we don't need any special presentations there. Okay, and this slide just reminds us everything. Yeah. Okay, so here's the definition of a relative group trisection. It's basically the same thing. It's a commutative cube, but now each of the homomorphisms is still a surjection. Each face is still a pushout. And one thing we do need to keep track of is I'm going to claim that these are 2 different letters. This is a W, that's an omega. And I want to make sure that my W's go to my omegas. And the idea behind that is if I'm constructing this cobordism, so if I just keep drawing this picture and compress along that alpha curve, well, up here I just get a disk, right, with no genus. And I just want to make sure that under this cobordism, this curve sort of still goes to this curve in general. And that's it. So that's the definition of a relative group trisection. And so the result that we have, so there's myself, Jason Joseph, and Patrick McFaddin. We extend the definition of this map M from the set of relative group trisections up to isomorphism to the set of relatively trisected diffeomorphisms. And they have the same composition where they compose to be the identities in their respective sets. Okay, good. And there's a key difference. I just want to point out a key difference in how we do this, and key difference from the closed setting. And we've sort of already touched on it a bit. And it's in this constructing of your cobordism. So we want to use one of these maps from over here, this group, these homomorphisms. We want to use each of those homomorphisms, SGB, to these groups to construct. And all this has to be unique to construct a cobordism from some high genus surface to some lower genus surface. right? But we also want to do it so that whenever we include our sort of trisection surface into this compression body, so let's call this compression body big C. If we include it into C, we must sort of induce the map H on pi1. Right, so however we include this into this compression body, we want to make sure that when we take pi1 of everything, we actually get the right homomorphism. And so that sort of is helped by sort of keeping track of all those generators in that group over there. So that's why we have to write everything down like that. Okay, so that's basically the idea of this construction and these maps. So it's really cool that like it's sort of this one-to-one correspondence, right? And we encode all this smooth four manifold data into just groups and their homomorphisms, which is really nice. And the other thing that we want to sort of understand is how the boundary comes into play. So I'm just going to mention a few things since I'm running out of time. So again, Kirby showed that a relative trisection induces an open book decomposition on the boundary. And in joint work with Dave Gay and Juanita Pinzon Caicedo, I showed that the diagram actually encodes this open book data. And we actually give an algorithm to find this open book. Right, so we have this sort of circle fibration over S1, or I'm sorry, surface bundle over S1. That's sort of recovered from this diagram. And I was going to draw the monodromy algorithm, but rather than do that, I'll just say that the diagram actually encodes it as sort of this arc, and it tells you what happens to that arc under the monodromy. So now we have this other thing. So this tells us that the open book is an annulus together with a Dane twist along the central curve. And that's all encoded in this picture right here. And so a question that we have is, how is this encoded in the group setting, right? Like it should encode everything. So where does this live? And I guess we're sort of not quite sure how to see this, because the problem is that this annulus, this is sort of the other end of the cobordism. And these arcs which live on them, well, they're not elements of pi1. So this annulus sort of doesn't live in any of these. I mean, it's in there, but it's not specifically one of these manifolds that we're taking pi1 of, and these arcs sort of aren't elements in these groups. So we have to do a little digging, and we have an idea of, we sort of know how we're going to deal with that, but not quite ready to say anything on that. But the idea is, we have this nice way to go back and forth between these two, and we just want to know like what goes here. Right. So of course we could always be given a group trisection, construct the four manifold, get the open book from the monodromy algorithm, and then we could just take pi1 of that 3 manifold. Right, and that goes there, and we also have sort of extra data from the open book. Right, so maybe I'll just write pi1 of open book. Maybe that goes here. So we can always do this, but we want to sort of do that directly. And so that's sort of where we are right now in sort of this whole construction. But with that, I think I will stop.
Let's thank Nick for the great talk. Are there any questions for Nick?
I have a question about this.
Yeah.
So on this last thing, so you have for these relative trisections, you get this open book structure. Is there any sort of relation with? Can you see any sort of statements in contact
That's
topology?
a great question, and I've been trying to find one for so long. Yeah, so some people recently, so Peter Lambert-Cole, Laura Starkson, Jeff Meyer, they wrote a paper on these Weinstein trisections of closed form manifolds. And I really was hoping that they could just like extend it to sort of like Stein manifolds with boundary inducing a certain open book, and then you could sort of they use this symplectic manifolds as branch covers over CP2, and I was really hoping that you could sort of branch the boundary over like a punctured CP2 and get like the contact structure that way, and then have everything fill in. But it seems like it's just difficult to do that. Yeah. But like given a Lefschetz fibration of a manifold with bounded fibers, you can get a relative trisection really easily, and it's a really easy way to just produce examples. And so in that setting, you sort of know sort of what the open book should be, and you can sort of hope to get some geometric data out of that as well. But so far, no luck.
So if I give you an open book, can you find, like, is there automatically? Oh no, sorry, it's a bad question. Anyways, yeah, it's a good answer. Thank you.
But if you give me an open book and you give it to me as sort of like Dane twists along a certain collection of curves, like ordered Dane twists, I can construct for you a filling of that three manifold that only consists of like attaching two handles. So you're basically just constructing the achiral Lefschetz vibration.
Following Kevin's question, so when you have an open book, like you can fill it by a chiral Lefschetz vibration, and is there like a canonical way to trisect that filling?
Yeah, there is, and I'll draw a picture for you really quick. Every time, so say here's the image of your Lefschetz singularity, and over here you have a neighborhood of your vanishing cycle. Let's make it orange. To trisect that, you do this perturbation, which is called wrinkling your singularity, and you actually get that trisection diagram of before that I drew before. But this is all in a neighborhood of your vanishing cycle. So if you have sort of some vanishing cycle which goes all over some crazy surface,